Look up at the night sky, and what do you see? Stars, planets, maybe a distant galaxy if you're lucky. But there's something far more mysterious hidden in the darkness between them. An invisible ocean stretches across the cosmos, a vast expanse of gas, dust, and energy so subtle we often forget it's there. This is the interstellar medium, the secret fabric of space itself, and it's teeming with puzzles that defy even the brightest minds. Think about it. Every time you gaze at the stars, you're looking through this ghostly veil, a cosmic frontier where temperatures swing from near absolute zero to millions of degrees, where particles thinner than a whisper somehow birth new worlds. What makes this hidden realm so fascinating isn't just its scale, it's the sheer number of questions it leaves unanswered. How does this diffuse soup of atoms and molecules collapse into fiery newborn stars? Why do certain regions glow with eerie light while others swallow radiation like a black hole? And what about the bizarre, unexplained signals that ping across the void, hinting at processes we can't yet comprehend? The interstellar medium isn't just empty space. It's a dynamic, chaotic playground where the laws of physics twist into shapes we're only beginning to map. That's exactly why we're diving deep into 25 of its most jaw-dropping mysteries today. From the enigma of dark matter's shadowy presence in the interstellar medium to the mind-bending ways magnetic fields sculpt entire galaxies, we're about to unravel secrets that will change how you see the universe. So buckle up, because this journey isn't just about distant clouds of gas. It's about peering into the hidden machinery of creation itself, where every discovery feels like uncovering a piece of the cosmos's best-kept diary. Ready to explore? Let's go. Imagine walking through a fog so thick you can't see your own hand, except this fog isn't made of water. It's an immense, invisible ocean of gas drifting between the stars, so elusive that even our most powerful telescopes struggle to find it. This is the enigma of dark gas, one of the interstellar medium's most baffling secrets. Unlike the glowing nebulas we often see in Hubble's breathtaking images, these shadowy clouds don't emit or reflect light. They're cosmic ghosts hiding in plain sight, yet holding clues to how galaxies evolve. So how do you find something you can't see? Astronomers had to get creative. By studying the way certain molecules like carbon monoxide absorb background starlight, or how cosmic rays interact with hidden hydrogen, they pieced together the presence of these colossal dark structures. What they discovered was staggering. These clouds aren't just scattered patches, they weave through entire galaxies, containing enough material to build thousands of stars. Yet their stealthy nature means we've likely underestimated just how much matter is lurking out there, silently shaping the cosmos. What makes dark gas truly mind-bending is how it defies expectations. For decades, scientists assumed the interstellar medium was either too hot or too diffuse to hide this much unseen material. But these clouds exist in a Goldilocks zone, cold enough to stay invisible, yet dense enough to influence star formation. Some even float near radiant nebulas like shadows cast by unseen giants. And here's the real kicker. If dark gas is more common than we thought, it could rewrite what we know about where and how planetary systems like ours are born. Now picture this: subatomic particles hurtling through space at nearly the speed of light, packing enough energy to rival a major league fastball, except these aren't baseballs. They're cosmic rays, and they've been bombarding Earth for over a century, leaving scientists scratching their heads about where they come from. These invisible bullets slice through the interstellar medium, their origins shrouded in mystery. Some are protons stripped from atoms, others are heavier atomic nuclei, and a few are even electrons whipped to unimaginable speeds. The puzzle begins with their sheer power. The most energetic cosmic rays carry millions of times more energy than anything we can produce in particle colliders like the Large Hadron Collider. That's like comparing a firecracker to a nuclear bomb. For decades, astronomers suspected supernova remnants, the expanding shockwaves from dying stars, as the main accelerators. Think of these remnants as cosmic pinball machines, where magnetic fields bounce particles back and forth until they're flung into space at breakneck speeds. But here's the catch: not all cosmic rays match the energy fingerprints expected from supernovas. Some are so energetic they must come from something far more extreme. Enter black holes, or more precisely, the colossal jets screaming from supermassive black holes at the hearts of galaxies. These jets, stretching thousands of light years, act like natural particle accelerators, potentially launching cosmic rays across the universe. Yet even this theory has gaps. While we've traced some lower-energy cosmic rays to nearby supernova remnants, the highest energy ones seem to arrive from all directions, making their sources nearly impossible to pinpoint. It's like trying to find a single flashlight in a stadium where everyone's shining lasers randomly. Adding to the confusion, cosmic rays don't travel in straight lines. The interstellar medium's tangled magnetic fields bend their paths, scrambling any clues about where they started. It's as if we're handed a letter with no return address and half the words smudged. To crack this case, scientists have turned to clever detective work, using observatories that detect the faint showers of particles cosmic rays create when they slam into Earth's atmosphere. But even these clues only deepen the mystery. Why do some cosmic rays arrive with energies that defy known physics? Could there be sources we haven't even imagined yet? One thing's certain: solving this riddle would rewrite our understanding of how the universe's most violent events shape the interstellar medium, and perhaps reveal entirely new cosmic phenomena hiding in the void. We've mapped distant galaxies, weighed black holes, and even detected the faint whispers of the cosmic microwave background, yet there's an embarrassing gap in our cosmic accounting books. Scientists call it the missing baryon problem, and it's one of the interstellar medium's most frustrating puzzles. Here's the issue: when we tally up all the normal matter, the atoms that make up stars, planets, and you, there's roughly half of it unaccounted for in today's universe. Not dark matter, not exotic particles, but regular protons and neutrons that should be lighting up our detectors. So where did it all go? The hunt for these lost atoms has led astronomers on a cosmic scavenger hunt through the vast stretches between galaxies. Picture the universe's structure like a spiderweb, with galaxies as glittering dewdrops clinging to the threads. Between those threads, an enormous reservoir of diffuse, superheated gas called the warm-hot intergalactic medium, or WIM. This stuff isn't just lukewarm, it's sizzling at millions of degrees, so hot it emits X-rays too faint for most telescopes to catch. Like steam rising from a highway, it's nearly invisible unless you know exactly where to look. Here's where things get clever. To spot this elusive matter, scientists turn to nature's own flashlights, distant quasars. As these brilliant beacons shine through the cosmic fog, their light gets subtly filtered by intervening gas. It's like holding a prism up to a spotlight. Specific wavelengths get absorbed, leaving chemical fingerprints in the quasar's spectrum. Patiently analyzing thousands of these absorption lines revealed tendrils of oxygen and nitrogen stretched between galaxies, confirming at least some of the missing matter is hiding in these ultra-thin filaments. But the plot thickens. Even after accounting for the WIM, there's still a discrepancy. Some theorists suggest the remaining atoms could be tied up in rogue planets, failed stars, or even vast clouds of molecular hydrogen too cold to emit detectable radiation. Others propose wilder ideas. Maybe the missing matter got ejected into deep space by galactic winds, or perhaps it's tucked away in microscopic quantum structures we can't yet perceive. What makes this mystery so critical isn't just the inventory slip, it's the implications. If we're fundamentally miscounting the universe's building blocks, our models of how galaxies form and evolve could be wildly off. Every uncounted atom means another gap in understanding how gravity sculpted the cosmos from primordial soup to the glittering web we see today. solving this riddle isn't just about finding lost matter. It's about rewriting the story of everything. Deep in the cosmic static, where radio waves whisper secrets across millions of light years, astronomers have stumbled upon something bizarre: colossal loops of energy, sprawling like celestial lassos across the galaxy. These aren't your average remnants of dead stars or the glow of star-forming gas. They're enormous filamentary structures, some stretching hundreds of light years end to end, pulsing with radio emissions no one fully understands. Picture throwing a stone into a pond and seeing ripples, except in this case, the pond is the Milky Way, and the ripples are brighter than entire star clusters. The most famous of these, the North Polar Spur, arcs high above our galaxy's disk, so vast it covers a quarter of the visible sky. At first glance, you might think it's just debris from an ancient supernova, a stellar explosion's final echo. But here's the twist: the energy signatures don't quite match. Supernova remnants usually fade over time, their radio emissions dwindling as they expand. These loops, they're too bright, too organized, as if something or someone left the cosmic lights on. Then there's the magnetism. The interstellar medium is threaded with invisible magnetic fields, but these loops seem to amplify them in ways that defy textbook physics. Imagine combing through a head of hair and suddenly finding a single strand that's glowing and humming with electricity. Some researchers suggest these loops could be magnetic reconnection sites, where cosmic field lines snap and realign, unleashing bursts of energy like solar flares, but on a galactic scale. Others speculate they're evidence of past galactic collisions, shockwaves frozen in time from long ago encounters with dwarf galaxies. But the wildest theories venture into uncharted territory. Could these loops be cosmic strings, hypothetical, ultra-dense defects in spacetime itself, left over from the Big Bang? Or perhaps they're the fingerprints of dark matter, interacting with normal matter in ways we've yet to comprehend. Every new observation deepens the puzzle. Recent studies even hint that some loops might be connected to gamma-ray bubbles, mysterious structures ballooning from the galaxy's core, adding yet another layer to the enigma. One thing's clear: whatever's sculpting these radio loops is operating on a scale we're only beginning to grasp. They're not just cosmic oddities, they're roadmaps to forces shaping the galaxy itself. Solving their riddle could rewrite how we understand everything from star formation to the very fabric of space. And until we do, they'll keep spinning their silent songs across the interstellar void. Shine a light through the cosmos and something strange happens. The starlight that reaches us carries hidden scars. Hundreds of faint, dark lines slice through the spectrum, as if something out there is siphoning away specific colors. These aren't the work of stars or planets. They're called diffuse interstellar bands, and they've been the interstellar medium's best-kept chemical secret for over a century. The craziest part: despite decades of hunting, we still don't know exactly what's causing them. The mystery began in the early 1900s when astronomer Mary Lee Hedger noticed peculiar gaps in the light from distant stars. These weren't the usual fingerprints of known gases like hydrogen or helium. Instead, they were unidentifiable, like finding suspicious footprints at a crime scene, but no suspect to match them. Today, we've catalogued more than 500 of these bands, each a unique clue pointing to molecules lurking in the void. But pinning them down, that's where things get messy. Imagine trying to identify a spice in a soup by tasting just one spoonful, except the soup is light years thick, and the spice could be any of millions of possible compounds. That's the challenge scientists face. The leading theory points to large, complex molecules called polycyclic aromatic hydrocarbons, or PAH. These carbon-based structures are everywhere in space, from soot to comet dust. But here's the hitch: lab experiments can't quite replicate all the diffuse band's signatures. It's like having a key that almost fits the lock but won't turn. Then there's the twist of cosmic chemistry. The interstellar medium is a brutal place: freezing temperatures, harsh radiation, and near-perfect vacuum. Most molecules would break apart instantly, yet whatever's creating these bands survives for eons. Some researchers speculate we're dealing with ultra-stable compounds like Fulleren's soccer ball-shaped carbon cages, or even exotic chains of linked atoms that don't exist on Earth. Others wonder if the bands come from shredded fragments of ancient organic material, the cosmic equivalent of confetti left over from stellar explosions. Every failed identification only deepens the intrigue. In 2021, astronomers thought they'd cracked it when they matched one band to a molecule called Buckminster-Fulleren. But the victory was short-lived. It explained just one line out of hundreds. The rest remained stubbornly silent, their origins wrapped in interstellar fog. Solving this puzzle isn't just academic. These mystery molecules could hold the recipe for how life's building blocks spread across the galaxy. Until then, those dark lines in starlight will keep taunting us, a cosmic barcode we're still learning to read. Take a handful of sand, shrink it 1,000,000 times, and toss it into deep space. What you'd get isn't just tiny rocks, but one of the interstellar medium's strangest residents. Interstellar dust grains are cosmic chameleons, defying every expectation we throw at them. Some are delicate, fluffy clusters barely held together. Others form razor-sharp crystalline structures, glittering like microscopic diamonds in the void. And here's the kicker: trapped inside them could be the very ingredients for life itself. Think of these grains as the universe's smallest architects. Floating between stars, they silently shape the birth of planets. When a cloud of gas and dust collapses to form a solar system, it's these specks that stick together, clumping into asteroids and eventually planets. But the process isn't as simple as stacking marbles. Some dust grains behave more like snowflakes, porous and fragile, riddled with tunnels and gaps that make them lighter than a soap bubble. Others are compact and metallic, forged in the furnaces of dying stars and blasted into space by supernovas. What baffles scientists is their sheer unpredictability. Under a microscope, they shouldn't survive. In the harsh environment of space, bombarded by radiation and battered by shock waves, fluffy grains ought to shatter instantly. Yet somehow they persist. Some theories suggest magnetic fields lock them in place, like invisible glue. Others propose static electricity binds them together, creating structures that defy conventional physics. And then there's the organic twist. Spectroscopic studies reveal eerie signatures of complex carbon-based molecules clinging to these grains. The implications are staggering. If dust can shelter organic material across interstellar distances, it could mean the building blocks of life hitchhike through the galaxy, seeding planets with probiotic chemistry. Imagine comets delivering these grains to early Earth, sprinkling our infant world with cosmic ingredients for biology. But mysteries remain. Why do some regions of space host dust that's jagged and crystalline, while others are fluffy and diffuse? Could these variations explain why some star systems form rocky planets, while others spawn gas giants? Every new telescope peering into dusty nebulas adds another piece to the puzzle. Recent images from the James Webb Space Telescope reveal microscopic crystals in the heart of stellar nurseries, glinting like frost in sunlight. Meanwhile, lab experiments attempt to recreate interstellar dust in vacuum chambers, bombarding synthetic grains with radiation to see how they evolve. The results: sometimes the grains grow stranger, not weaker, hinting that space itself might sculpt them into shapes we've yet to imagine. One thing's clear: these microscopic specks hold macroscopic secrets. They're not just debris, they're time capsules carrying stories of stellar explosions, chemical evolution, and perhaps even the origins of life. Until we crack their code, the universe's tiniest builders will keep whispering riddles from the dark. The interstellar medium might seem like a chaotic, formless void, but there's an invisible sculptor at work, bending it into shape with forces we can't even see. Magnetic fields, weaker than a fridge magnet yet vast enough to span galaxies, are the universe's silent puppet masters. They twist gas into intricate filaments, steer collapsing clouds into newborn stars, and even funnel cosmic rays across unimaginable distances. But here's what keeps scientists up at night. No one knows exactly how these fields got so strong, or why they behave in ways that defy our best models. Picture a star being born. Gravity pulls a cloud of gas together, but without magnetic fields, that cloud would collapse into a messy, chaotic blob. Instead, what we see are elegant, spinning disks, cosmic nurseries where planets eventually form. That's because magnetic fields act like cosmic guide wires, channeling material into orderly structures. They're the reason star-forming regions look like swirling storms, with tendrils of gas spiraling inward like water down a drain. But the mystery deepens when we measure their strength. Some regions have fields so powerful they shouldn't exist according to classical physics. In places like the Taurus molecular cloud, magnetic pressure rivals gravity itself, putting the brakes on star formation in ways we still can't fully predict. Then there's the question of origin. Most theories suggest these fields started as faint seed fields, amplified over billions of years by the motion of ionized gas, a process called the dynamo effect. Imagine stirring a cup of coffee with a tiny magnet at the bottom. Given enough time, the swirling motion could theoretically strengthen the field. But here's the flaw. The universe hasn't had enough time for this process to explain the colossal fields we observe. Some regions show coherent magnetic structures stretching hundreds of light years, as if someone stretched a cosmic rubber band across the void. Even stranger are the field reversals, places where the magnetic polarity flips unexpectedly, like a section of the Milky Way's spiral arm where the field suddenly does a U-turn. These anomalies suggest something far more dynamic is at play, possibly linked to ancient galactic collisions or eruptions from supermassive black holes. Recent simulations hint that turbulence in the interstellar medium might twist and braid magnetic lines like tangled yarn, creating pockets of intense energy. But without direct observations, these ideas remain stuck in the realm of theory. What's at stake isn't just an academic curiosity. Magnetic fields could hold the key to some of astrophysics' biggest puzzles. From why galaxies have their distinctive shapes to how life's building blocks hitchhiked across the cosmos. Some researchers even speculate that these fields might interact with dark matter, weaving an invisible web that guides the growth of the universe itself. Until we crack their code, we're missing a fundamental chapter in the story of how emptiness gives birth to everything. At the very edge of our solar system, where the sun's influence fades to a whisper, something unexpected lurks, an invisible barrier of hydrogen piled up like cosmic driftwood along a shoreline. These so-called hydrogen walls aren't just passive clouds, they're dynamic structures detected by their faint ultraviolet glow as spacecraft like New Horizons peer into the abyss. What's baffling is how they got there. One theory suggests they're the debris from ancient supernova, shock waves that slammed into the heliosphere and left behind a molecular echo. Others propose something far stranger, that these walls are evidence of an unseen tug of war between the solar wind and the interstellar medium itself. Imagine the heliosphere, that protective bubble of charged particles blown by the sun, as a ship plowing through an ocean of galactic gas. Where the bow of this cosmic vessel meets the interstellar current, hydrogen atoms pile up, slowed by the pressure like foam gathering at the prow. But here's the twist: the walls are thicker and more structured than they should be. If they were just passive accumulations, their density would drop off smoothly. Instead, they clump in uneven layers, as if something, perhaps magnetic fields or hidden turbulence, is sculpting them into shape. Then there's the puzzle of their composition. Spectroscopic data reveals these hydrogen walls are laced with trace amounts of heavier elements like oxygen and neon. That's a smoking gun. Supernova spew these elements into space, suggesting the walls might be relics of stellar explosions that rocked our galactic neighborhood millions of years ago. Picture a tsunami of debris crashing into the heliosphere, leaving behind a fossilized imprint. Yet not all the evidence fits. Some regions of the walls glow too brightly for simple stellar remnants, hinting at ongoing energy exchange with the interstellar medium. The most tantalizing possibility: these walls could be the first tangible evidence of how the interstellar medium reshapes planetary systems. As the Sun orbits the galaxy, it doesn't move through a uniform void. It wades through rivers of denser gas, dodges pockets of ionized plasma, and maybe even punches through rogue molecular clouds. Each encounter leaves a mark, and the hydrogen walls might be the latest chapter in that story. If so, studying them could reveal how often stars like ours collide with interstellar weather, and what that means for life on planets huddled under their heliospheric shields. For now, the walls keep their secrets. New Horizons' ongoing journey, coupled with future missions like Interstellar Probe, aims to map these structures in unprecedented detail. What they find could rewrite our understanding of where the solar system ends and where the true wilderness of the galaxy begins. Deep in the coldest corners of space, where temperatures hover just a few degrees above absolute zero, something extraordinary clings to the surfaces of dust grains, thin, fragile layers of ice. Not the kind you'd find in your freezer, but exotic blends of water, methane, ammonia, and even carbon monoxide frozen into a glassy matrix. These interstellar ices are more than cosmic frost. They're chemical factories quietly assembling molecules that might one day spark life. And the wildest part, under the right conditions, these ices can transform simple atoms into the building blocks of biology. Take a single grain of dust drifting through a molecular cloud. At first glance, it seems inert, but its icy coating is anything but. Bombarded by ultraviolet light from nearby stars and zapped by cosmic rays, the ice undergoes a silent alchemy. Radiation breaks apart molecules, creating free radicals, highly reactive fragments that scurry across the surface like molecular ghosts. When they collide, new compounds form. Formaldehyde, hydrogen cyanide, even amino acids have all been detected in lab experiments that simulate these conditions. It's as if the universe is running chemistry experiments in deep freeze, with ice as both crucible and catalyst. But how do these processes survive the chaos of space? The answer lies in the ice's bizarre structure. Unlike the orderly crystals in your ice cube tray, interstellar ice is amorphous, a disordered, porous mess riddled with tunnels and pockets. These nanoscale labyrinths trap molecules, giving them time to react despite the harsh environment. Some ices also contain clathrates, cage-like structures that imprison gas molecules like methane, shielding them from destruction. Imagine a sponge made of ice, soaking up the raw ingredients for life and holding them safe for millions of years. The implications are staggering. When a molecular cloud collapses to form a star, these icy grains get dragged along, eventually becoming part of comets, asteroids, and planets. Experiments show that when warmed, say, by the heat of a young star, the ice releases its stored chemicals, potentially drenching newborn worlds in prebiotic soup. The Rosetta mission's discovery of organic molecules on comet 67P Churyumov-Gerasimen co-supports this idea. The building blocks of life might have hitchhiked to Earth on icy visitors from deep space. Yet mysteries remain. Why do some molecular clouds produce complex organics while others seem sterile? Could magnetic fields or cosmic rays determine which ices form and survive? Recent observations with the James Webb Space Telescope have spotted ices containing alcohols and ethers, molecules previously thought too fragile for space. Each finding adds another piece to the puzzle, suggesting that the universe's icy frontiers are far more chemically inventive than we ever imagined. What's clear is this: the frosty coatings on interstellar dust aren't just frozen water. They're cosmic test tubes quietly brewing the ingredients for life in the darkness between the stars. And if we're right, every planet, perhaps every living thing, owes its existence to these unassuming sheets of ice. Look closely at certain patches of the interstellar medium, and you'll find something bizarre: vast, spherical voids where gas and dust seem to have been scooped out like cosmic ice cream. These empty bubbles stretch dozens or even hundreds of light years across, their walls glowing faintly with compressed material while their interiors appear eerily vacant. But here's the catch: nothing in space is ever truly empty. So what's really going on inside these ghostly orbs, and what cosmic force has the power to hollow out regions so large they could swallow entire star clusters? The leading theory points to the brute force of stellar winds. Picture a massive, short-lived star. Think of a blue supergiant burning furiously with the energy of a million suns. These stars don't just shine, they scream. Their solar winds blast outward at speeds topping millions of miles per hour, shoving surrounding gas aside like a snowplow clearing a highway. Over thousands of years, these winds carve out colossal cavities, leaving behind bubbles that linger long after the star itself has died. Supporting this idea, astronomers have spotted young, hot stars centered in some bubbles, their furious outflows visibly warping the surrounding medium. But not all bubbles fit this neat explanation. Some appear in regions devoid of obvious stellar culprits, their origins shrouded in mystery. That's where supernovae enter the picture. When a massive star explodes, it doesn't just vanish. It unleashes a shockwave so powerful it can evacuate a sphere of gas hundreds of light years wide. The Crab Nebula's progenitor star, for instance, likely blew a bubble visible from Earth in the year 1054. Yet even supernovae struggle to explain the most gargantuan voids, some of which span over 1,000 light years. This discrepancy has led to wilder possibilities. Could these bubbles be the work of rogue black holes tunneling through gas clouds as they devour matter? Or perhaps collisions between entire molecular clouds, where the sheer kinetic energy of impact punches holes in the interstellar medium? The most radical theory suggests some voids might be relics of dark matter interactions, regions where invisible particles annihilated each other, releasing energy that cleared out normal matter. What makes these bubbles truly fascinating isn't just their formation, but their afterlife. Over millions of years, their expanding walls can trigger star formation by compressing surrounding gas, like a snowball rolling downhill, gathering material until it collapses under its own weight. Some astronomers even speculate that our own solar system might owe its existence to such a bubble, born from an ancient supernova that sculpted the local interstellar medium just as the Sun was forming. Until we peer deeper into these phantom voids, they'll remain one of the interstellar medium's most tantalizing riddles, silent, hollow monuments to the universe's untamed forces. Hidden in the interstellar medium's shadowy depths could be an entire class of molecules that refuse to play by the usual cosmic rules, ones that don't absorb, emit, or even reflect light. These aren't your typical gas clouds or dust grains. They're theoretical constructs known as dark molecules, and they might hold the key to one of astronomy's biggest headaches, the missing mass problem. If they exist, they'd be the ultimate cosmic ninjas, slipping past every telescope we've ever built. So how do you find something that leaves no trace? The first clue lies in gravity. Just like dark matter betrays its presence by tugging on stars and galaxies, dark molecules could reveal themselves through their subtle gravitational influence. Picture a dense molecular cloud where the math says there should be a certain amount of material, yet traditional observations like radio waves or infrared signatures only account for a fraction of it. That discrepancy might hint at invisible molecules lurking in the void. Some scientists speculate these could be exotic hydrogen-based compounds, like paired proton clusters or bizarre quantum states of matter that don't interact with electromagnetic radiation at all. But gravity alone isn't enough to crack the case. Enter cosmic chemistry's detective tools, indirect signatures. Even if dark molecules don't absorb starlight, their presence could perturb the behavior of normal matter around them. Imagine walking through a pitch-black room and sensing obstacles by the way air currents shift around them. That's essentially what astronomers do when they study minute distortions in the spectra of known molecules. Unexplained line broadening or frequency shifts in carbon monoxide emissions, for instance, might betray the gravitational nudges of unseen neighbors. The real twist: some dark molecules might not be entirely dark. Certain theoretical particles, like action-like particles or magnetic monopoles, could interact weakly with magnetic fields or other hidden forces in the interstellar medium. These interactions could leave faint fingerprints in the polarization of starlight or the alignment of dust grains, subtle hints that next-generation telescopes like the Square Kilometre Array might one day spot. What's at stake isn't just a catalogue of cosmic ghosts. If dark molecules make up even a small fraction of the missing mass, they could redefine how stars and planets form. Current models assume collapsing gas clouds are governed by known physics, but toss in a hidden component, and suddenly, the math behind stellar nurseries gets a lot more complicated. Maybe these elusive particles act as cosmic glue, stabilizing gas clouds that would otherwise fragment too quickly. Or perhaps they're the reason some regions of space seem to resist star formation altogether, like invisible speed bumps in the path of gravity's collapse. The hunt is still in its infancy, but the implications are staggering. If dark molecules exist, they could bridge the gap between ordinary matter and the enigmatic realm of dark matter, offering a tantalizing glimpse into the universe's hidden architecture. Until then, they remain one of the interstellar medium's most provocative mysteries, a cosmic game of hide and seek where the hiders might not even leave footprints. The interstellar medium is supposed to be a wasteland so empty, so cold, that chemical reactions should grind to a near standstill. Yet somehow, against all odds, it's brewing cocktails of complex molecules that leave scientists baffled. We're not just talking simple water or carbon monoxide. Out there, in the freezing void between stars, astronomers have found everything from ethanol, the same alcohol in your beer, to formaldehyde, acetone, and even sugar molecules. These discoveries shatter our assumptions about chemistry in space because, according to textbook rules, these reactions shouldn't happen at all. So what's really cooking in the cosmic kitchen? Take glycine, the simplest amino acid and a building block of life. For decades, scientists argued it couldn't form in space. The math said so molecules that complex need liquid water or dense environments to assemble, and the interstellar medium offers neither. Yet in 2020, the Rosetta mission found it on Comet 67P, and radio telescopes have since detected its chemical cousins floating in nebulas. The answer: dust grains. Those tiny specks we once thought were inert turn out to be bustling chemical factories. When a molecule like formaldehyde lands on a grain's surface, the frigid temperatures, just 10 degrees above absolute zero, should freeze it in place. But here's the twist: cosmic rays and ultraviolet light provide just enough energy to nudge atoms into unholy alliances, crafting compounds that defy conventional chemistry. Then there's the mystery of acetone. In 2019, researchers spotted vast clouds of it near the center of our galaxy, enough to fill billions of swimming pools. On Earth, acetone forms through biological processes or industrial reactions requiring heat and pressure. In space, no factories, no life, just the eerie efficiency of radiation-driven chemistry. Similar puzzles surround ethanol, which lurks in molecular clouds in quantities that would make a distillery blush. Some of these clouds contain enough alcohol to supply every human on Earth with 300,000 drinks a day for billions of years. The kicker: no one knows exactly how these molecules grow so large in near-vacuum conditions. The plot thickens when you consider chiral molecules, compounds that come in mirror image versions like left and right-handed gloves. On Earth, life overwhelmingly uses one type, but in space, both forms should appear equally. Yet recent studies suggest some interstellar molecules might show a slight preference, hinting at processes that could have seeded life's asymmetry. Could the seeds of biological handedness have been planted in the void long before Earth formed? What's clear is this: the interstellar medium isn't just a passive backdrop. It's a dynamic, unpredictable chemist whipping up compounds we've barely begun to catalog. Solving these riddles could rewrite not just our understanding of space, but the origins of life itself. For decades, astronomers have been haunted by a faint crimson glow that permeates the cosmos, a phenomenon so subtle it was almost missed entirely. Known as extended red emission or ER, this mysterious light paints the interstellar medium with an eerie, diffuse hue, stretching from the visible spectrum well into the infrared. Unlike the vibrant colors of nebulas or the sharp emission lines of gases, ER is a broad, smooth wash of red, as if someone smeared a cosmic watercolor across the void. The strangest part, we still can't say for certain what's causing it. One leading suspect is a class of carbon-based molecules called polycyclic aromatic hydrocarbons, or PAH. These flaky, soot-like structures are everywhere in space, remnants of dying stars and the building blocks of interstellar dust. When hit by ultraviolet light, PAHs can fluoresce, re-emitting energy at longer wavelengths, just like the red glow we see. But here's the snag: lab experiments show PAHs usually emit in the infrared, not the broad red band of ER. It's as if we've found a witness at the scene, but their alibi doesn't quite hold up. Then there's the nanodiamond hypothesis. Imagine microscopic diamonds forged in the hearts of supernova and scattered across the galaxy like cosmic confetti. These tiny crystals have unique optical properties, and under the right conditions, they could theoretically produce ER signature glow. Some studies even point to specific spectral fingerprints that match lab-created nanodiamonds. But the mystery deepens when we consider the sheer scale of ER. It's everywhere, from star-forming regions to the quietest corners of interstellar space. Are there really enough nanodiamonds out there to account for all that light? The numbers teeter on the edge of plausibility. The wild card, an entirely unknown type of particle or physical process. Some theorists suggest ER could come from quantum dot semiconductor fragments so small they trap electrons in discrete energy states, forcing them to emit light at specific wavelengths. Others wonder if we're seeing the handiwork of graphene flakes, sheets of carbon just one atom thick, curling and warping in ways that alter their glow. And then there's the tantalizing possibility that ER is a side effect of dark matter interactions, a faint echo of particles we've yet to discover. What makes this enigma so compelling isn't just the light itself, but what it tells us about the interstellar medium's hidden complexity. ER isn't a fluke, it's a fundamental feature of our galaxy, a whisper of chemistry playing out on scales we're only beginning to grasp. Solving it could reveal new pathways for molecule formation, or even rewrite how we think about cosmic dust's role in shaping the universe. Until then, that ghostly red glow remains one of space's most persistent riddles, a silent, shimmering question mark hanging in the dark. Lithium should be everywhere in the cosmos. After all, it was forged in the fiery chaos of the Big Bang alongside hydrogen and helium, one of the universe's original ingredients. But when astronomers tally up the lithium in the interstellar medium today, something doesn't add up. The numbers are staggeringly low, as if some cosmic thief has been quietly siphoning it away. Where did it all go? This isn't just a minor accounting error. It's a gaping hole in our understanding of how elements cycle through the galaxy. The first clue to this vanishing act came from studying ancient stars. These celestial relics, born when the universe was young, contain lithium levels that match Big Bang predictions almost perfectly. Yet when we look at younger stars and the gas between them, the numbers plummet. It's like finding a pantry full of flour in Grandma's century-old kitchen, only to discover the modern supermarket shelves are nearly bare. Clearly, something's been destroying lithium over time or hiding it in plain sight. One leading theory points the finger at stars themselves. When lithium drifts too close to a star's searing interior, it meets a brutal fate. At temperatures above 2 million degrees, lithium nuclei are torn apart, fused into heavier elements like helium. It's the cosmic equivalent of tossing ice cubes into a blast furnace. Red giants in particular seem to be lithium graveyards. Their outer layers often show depleted amounts, as if they've been burning through their reserves for eons. But here's the twist. Even if every star in the galaxy were incinerating lithium at maximum efficiency, the math still doesn't account for all the missing atoms. There must be another culprit at work. That's where the interstellar medium's hidden chemistry comes in. Lithium is a flighty element, light, reactive, and prone to odd behavior. In the cold reaches of space, it could be clinging to dust grains, forming compounds like lithium hydride that are invisible to traditional telescopes. Imagine sprinkling salt into a snowbank. From a distance, you'd never spot it, even though it's still there. Some researchers speculate that lithium might even be hiding in tiny molecular clusters, microscopic structures too small to detect with current instruments. But the most tantalizing possibility involves cosmic rays. When high-energy particles slam into interstellar gas, they can shatter lithium nuclei like glass, transforming them into isotopes that decay rapidly or fuse into other elements. This process, called spallation, could be stealthily erasing lithium from the galactic inventory. Supporting this idea, astronomers have found spikes of beryllium and boron elements typically forged in cosmic ray collisions, in regions where lithium is conspicuously absent. It's like finding broken locks and scattered jewels near a burglar's hideout. The stakes here are higher than just solving a chemistry puzzle. Lithium is a key piece of the cosmic abundance ladder, a diagnostic tool scientists use to test theories about the Big Bang and stellar evolution. If we're missing something fundamental about how it behaves, other parts of our cosmic model might be on shaky ground. Future telescopes, like the extremely large telescope in Chile, could finally crack this case by hunting for lithium's spectral fingerprints in the thinnest, coldest corners of the interstellar medium. Until then, this lightweight element's vanishing act remains one of the most persistent and perplexing mysteries in the galaxy. Molecular clouds should be cosmic assembly lines, orderly places where gravity slowly pulls gas together until stars ignite. But reality is far messier. Some regions collapse in frenzied bursts, spawning stars at breakneck speed, while others linger in a frozen limbo for millions of years, resisting gravity's pull like a stretched rubber band refusing to snap. What's tipping the scales in these stellar nurseries? The answer might lie in forces we're only beginning to trace. Take the Taurus molecular cloud, a textbook case of cosmic procrastination. Packed with enough gas to form hundreds of stars, it's produced barely a handful. Conventional models say it should have collapsed long ago. Gravity's tug is relentless after all. Yet something's holding it back. Magnetic fields are the prime suspects. Weaving through the cloud like invisible threads, these fields exert pressure that can counterbalance gravity, propping up gas clumps like scaffolding. The catch: measurements show the fields in Taurus are 10 times stronger than predicted, as if the universe cranked up a hidden dial. Even stranger, pockets of turbulence within the cloud seem to defy the fields, creating chaotic eddies where star formation sparks erratically. It's a cosmic showdown, magnetism versus chaos, with stellar births hanging in the balance. Then there's the opposite extreme, places like the Orion Nebula, where stars erupt in furious clusters. Here, gravity isn't just winning, it's sprinting. The culprit: feedback loops from newborn stars themselves. When massive stars ignite, their fierce radiation and solar winds blast through the surrounding gas, compressing nearby regions into dense knots that collapse faster. It's a stellar domino effect. One birth triggers others, creating chains of star formation that spread like wildfire. But even this explanation has holes. Some hyperactive clouds lack obvious trigger stars, suggesting hidden drivers, perhaps shock waves from ancient supernova or collisions with invisible dark matter filaments. The wild card in all this: cosmic rays. These high-energy particles zipping through the interstellar medium might be the unseen puppeteers. By ionizing gas molecules, they could strengthen magnetic fields in some areas while weakening them in others, creating patchwork conditions for star birth. Imagine a gardener selectively watering patches of soil. Some seeds sprout wildly while others lie dormant. Recent observations of clouds like Rho Ophiuchi support this idea, showing eerie correlations between cosmic ray fluxes and star formation rates. What's clear is this: molecular clouds aren't passive factories. They're dynamic, moody ecosystems where unseen forces, magnetism, turbulence, radiation, wage silent wars. Crack their secrets and we'll finally understand why the universe builds stars on its own unpredictable schedule. Out in the interstellar medium, where atoms drift lazily at speeds you could outpace on a bicycle, there's a group of renegade molecules breaking all the rules. These aren't your typical slow-moving particles. They're cosmic speed demons, whipping through space faster than physics should allow. Take simple molecules like silicon monoxide, often found near dying stars. Under normal conditions, they'd move at a sedate pace dictated by temperature, like leaves floating on a pond. But astronomers keep catching these molecules red-handed, zooming at velocities that would require temperatures of thousands of degrees, except their surroundings are barely warmer than absolute zero. It's as if someone strapped tiny rockets to them and fired them into the void. So what's launching these molecular projectiles? One compelling suspect lurks everywhere in the interstellar medium: tangled magnetic fields. Picture a molecule as a tiny compass needle. In the presence of a strong magnetic field, charged atoms can get caught in a slingshot effect, accelerated along field lines like beads on a wire. This might explain why some molecules near supernova remnants move in coordinated jets, as if they've all hitched a ride on the same invisible highway. But here's where the theory hits turbulence. Some of these speedy molecules show no clear connection to magnetic hotspots, darting through calm regions of space where fields are whisper weak. That's led researchers to more exotic possibilities. Could these molecules be surfing on shockwaves from ancient stellar explosions we haven't detected? Or perhaps they're the fallout from microscopic black holes evaporating in a burst of energy, a phenomenon predicted by quantum physics but never observed. The wildest hypothesis involves cosmic strings, hypothetical spaghetti-thin defects in space-time left over from the Big Bang. If they exist, their immense gravitational pull could fling molecules to impossible speeds without leaving visible traces. The implications ripple far beyond a few rogue particles. If magnetic fields are more efficient accelerators than we thought, they could be secretly shaping how molecules distribute across galaxies. Alternatively, if something stranger is at work, it might hint at new physics hiding in plain sight. Every time a telescope catches another impossibly fast molecule, it's like finding a fingerprint at a crime scene, one that could belong to a suspect we've never met. Until we solve this case, the interstellar medium speedsters will keep racing through the cosmos, taunting us with the secrets tucked into their breakneck trajectories. Carbon shouldn't stand a chance in the interstellar medium. Floating in a sea of radiation, ultraviolet light-shredding molecules, cosmic rays smashing atoms, it ought to be torn apart faster than it can form. Yet somehow, against all odds, carbon chains thrive out there. Not just simple ones, but sprawling, complex structures that shrug off conditions that would vaporize most molecules. How do they do it? This isn't just a chemistry puzzle, it's a cosmic survival story, and the answer might rewrite what we know about the building blocks of life. Picture a carbon chain drifting through space, a fragile thread of atoms linked like beads on a string. When a UV photon slams into it, the energy should snap bonds instantly, leaving behind broken fragments. But astronomers keep spotting these chains intact in places like the Taurus molecular cloud, where radiation floods every corner. One theory suggests they're not just tough, they're self-healing. Lab experiments show that when certain carbon chains break, the dangling ends can rebind in microseconds, like a zipper closing itself. Some even grab passing hydrogen atoms to patch damage, turning lethal radiation into a repair tool instead of a death sentence. Then there's the cloak and dagger hypothesis. Carbon chains might be hiding in plain sight, shielded by cloaks of ice or dust. Imagine wrapping a glass sculpture in bubble wrap before tossing it down a staircase. The protection changes everything. In the icy mantles of interstellar grains, carbon structures could weather radiation storms unharmed, only emerging when conditions calm. Spectroscopic data supports this. Some dense clouds show carbon molecules peeking out once surrounding gas blocks the harshest light. But the real curveball comes from an unexpected ally, chaos itself. Turbulence in the interstellar medium creates fleeting pockets where temperatures and densities spike, allowing broken chains to reassemble faster than radiation can finish them off. It's like trying to demolish a sandcastle while waves constantly rebuild it. Recent simulations reveal these chaotic zones might act as carbon nurseries, where destruction and rebirth happen in a frenzied dance. What makes this mystery so urgent isn't just the survival of carbon, it's what comes next. These chains are the stepping stones to polycyclic aromatic hydrocarbons, the very molecules that might have seeded life on Earth. If carbon can outwit the universe's worst assaults, it could mean the galaxy is littered with life's raw materials, tougher and more widespread than we ever dreamed. Until we crack their secrets, these unkillable molecules will keep drifting through the void, silent witnesses to a resilience we're only beginning to understand. Deep in the cosmic static, where radio telescopes sift through the noise of the universe, there's a signal that shouldn't exist, pulses of microwave light so intense they outshine stars, flashing like interstellar lighthouses with no visible source. These aren't your typical cosmic emissions. They're cosmic masers, nature's own microwave lasers, amplifying light into beams so focused they could punch through galactic dust without scattering. But here's what keeps scientists up at night. Some of these signals arrive with no obvious cosmic engine behind them, whispering secrets about processes we've yet to imagine. Masers themselves aren't new. We've spotted them flaring in star-forming regions where swirling gas and newborn stars create perfect conditions to amplify microwave light. Picture a cloud of water molecules energized by a young star's radiation, emitting photons in perfect lockstep, like an army of synchronized swimmers creating a wave. But the real enigma lies in the rogue masers, the ones flickering in quiet pockets of the interstellar medium where no stars are being born. These signals are too powerful, too erratic, as if something or someone is tweaking the cosmic dials. Theories abound. Some suggest these masers trace hidden stellar nurseries buried under thick veils of dust, their visible light completely obscured but their microwave fingerprints slipping through. Others propose more exotic origins, collapsing molecular clumps where gravity's crush excites molecules to laser-like coherence, or even shock waves from ancient supernova rippling through gas clouds like a stone skipping across a pond. Then there's the wild card. Could some masers be artificial? The idea isn't as far-fetched as it sounds. A sufficiently advanced civilization might use masers for communication or propulsion, their signals standing out against nature's backdrop like a flare in fog. What makes these whispers so tantalizing is their precision. Unlike the chaotic scatter of radio emissions from pulsars or quasars, maser signals are razor-sharp, with spectral lines so narrow they reveal details about the gas clouds they pass through, temperature, density, even magnetic fields. It's like eavesdropping on the universe's private conversations. Recent observations of megamasers' colossal versions of these phenomena in other galaxies hint that they might trace the gravitational dance of supermassive black holes, their flickering patterns encoding motions too subtle to see any other way. Yet for every answer, these microwave ghosts pose new questions. Why do some regions with identical conditions produce masers while others stay silent? How can certain molecules like hydroxyl or methanol sustain such intense amplification without collapsing under their own energy? And could there be an entire population of dark masers out there, their signals so faint or infrequent we've barely caught glimpses? Solving these riddles won't just satisfy curiosity, it could redefine how we map the invisible skeleton of the cosmos, one microwave whisper at a time. Helium, the universe's second most abundant element, should be everywhere, floating freely in the interstellar medium, mingling with hydrogen like an old friend. Yet something strange is happening in certain pockets of space. When astronomers measure the ratio of helium to hydrogen, the numbers don't add up. In some regions, helium seems to vanish into thin air, leaving behind a cosmic deficit that defies expectations. Where could it be going? The answer might rewrite what we know about how elements hide or disappear in plain sight. One possibility is that helium isn't vanishing at all, it's just playing hide and seek. Unlike hydrogen, which forms visible molecules or emits detectable radio waves, helium is a lone wolf. It doesn't easily bond with other elements, and it's notoriously shy when it comes to emitting or absorbing light. In cold, dense clouds, helium could be sinking to lower layers, settling beneath hydrogen like oil floating on water. Telescopes peering at these regions might only catch the hydrogen's glow, completely missing the helium lurking just out of sight. It's like searching for a clear marble in a snowbank. Unless you know exactly where to look, it's practically invisible. But there's a wilder theory: something out there is eating helium. Not literally, of course, but certain processes could be locking helium away in forms we can't easily detect. Take dust grains, for example. Under extreme pressures, helium atoms might get trapped inside microscopic cages of carbon or silicate, clinging to dust like burrs on a sweater. Even more intriguing is the idea of helium hydride, a fragile molecule of helium and hydrogen that only forms under conditions so rare it was once thought impossible in space. Yet in 2019, astronomers finally spotted it in a planetary nebula, proving helium isn't always a solo act. If helium hydride exists in more places than we've found, it could explain why some of the universe's helium has gone off the grid. Then there's the dark horse of the mystery: stellar winds. Massive stars spew helium-rich gas into space, but not all of it stays there. Turbulent flows and magnetic fields might funnel this helium into narrow streams or hidden pockets, redistributing it unevenly across the interstellar medium. Imagine blowing on a cup of hot cocoa. The steam carries away heat, but not uniformly. Some areas get scalded while others stay cool. Similarly, helium might be concentrated in regions we're not yet observing, leaving behind gaps that look like shortages. The stakes here are higher than just balancing cosmic ledgers. Helium is a key ingredient in star formation, acting as a coolant that helps gas clouds collapse into new suns. If it's disappearing or hiding in ways we don't understand, our models of how stars are born could be missing a critical variable. Even more tantalizing is the prospect that this helium deficit hints at undiscovered physics. Perhaps interactions with dark matter or quantum behaviors we've yet to uncover. Until we solve it, the vanishing helium problem remains a quiet enigma, a cosmic magic trick where the universe's second most famous element keeps slipping through our fingers. The coldest places in the universe aren't where you'd expect, not in the frozen voids between galaxies, not in the shadow of distant planets, but right here in our own interstellar backyard. Astronomers have stumbled upon pockets of the interstellar medium so cold, they defy the very laws of physics as we know them. These phantom cold spots dip just a hair above absolute zero, the temperature where all motion theoretically stops. But here's the kicker: according to our models, regions this frigid shouldn't exist naturally. So what's plunging these cosmic freezer zones into such impossible cold? One clue lies in their eerie uniformity. These cold spots aren't scattered randomly. They often appear as perfect spheres or elongated filaments, like frost creeping along a window pane. That precision hints at something more than simple cooling. Some theorists suggest they could be cosmic shadows, regions where an unseen force, dark matter perhaps, is siphoning away thermal energy like a celestial vampire. Others propose even wilder ideas. What if these zones are bruises left by collisions with parallel universes? The concept, called the bubble universe theory, suggests our cosmos might occasionally bump against neighboring dimensions, transferring energy in ways that leave behind these bizarre thermal scars. But before we jump to multiverse conclusions, there's a humbler possibility. Our models are broken. Traditional thermodynamics assumes gas in space cools evenly, like steam dissipating from a kettle. But what if certain molecular structures like ultra-fine dust or exotic quantum states act as thermal sponges, soaking up heat far more efficiently than we've accounted for? Lab experiments with superfluids, liquids that flow without friction, show similar extreme cooling behaviors under specific conditions. Could the interstellar medium be hiding its own version of these quantum oddities? The implications stretch beyond academic curiosity. If these cold spots are nature's way of breaking our temperature rules, they could revolutionize how we understand heat transfer in space, affecting everything from star formation to the design of future deep space probes. Alternatively, if they really are windows into other realities, we might be standing on the threshold of the greatest paradigm shift in cosmology since relativity. Until we crack this icy enigma, these cold spots will keep floating through the darkness, silent and unnerving, like cosmic breadcrumbs leading to truths we're not yet ready to face. Buried in the chemistry of the interstellar medium are faint echoes of stellar apocalypses, explosions so violent they briefly outshone entire galaxies. These are the fingerprints of ancient supernova, long-dead stars that seeded space with their ashes. But what's astonishing isn't just their past fury, it's how they continue to sculpt the galaxy millions of years later, whispering secrets through the atoms they left behind. Take iron, for instance. Every speck of iron in your blood, every steel skyscraper on Earth, was forged in the heart of a dying star and blasted into space by a supernova. When astronomers scan the interstellar medium, they find this elemental confetti scattered unevenly, concentrated in bizarre tendrils and bubbles. Some regions, like the local bubble surrounding our solar system, are practically iron-rich neighborhoods, cosmic suburbs built on the debris of stellar catastrophes that occurred millions of years ago. The twist: these elements don't just linger passively. They act as cosmic catalysts, altering how gas cools, collapses, and eventually ignites into new stars. Then there's the mystery of orphan isotopes, radioactive elements like aluminum-26 that shouldn't exist in the interstellar medium today. With half-lives of just a few 100,000 years, their presence is like finding a still-warming teacup in an abandoned house. They're the smoking gun of recent supernova, ones that might have detonated close enough to shower our corner of the galaxy with fresh debris. In 2022, researchers found traces of iron-60 in Antarctic snow, a radioactive isotope only produced in supernova, proving Earth was dusted with stellar shrapnel as recently as 3 million years ago. If such events keep happening, the interstellar medium isn't just a graveyard for dead stars. It's an active crime scene still being reshaped by celestial violence. But the real enigma lies in the shadows. Some regions of the interstellar medium show bizarre chemical imbalances: too much oxygen here, too little sulfur there, as if entire layers of supernova debris were peeled away by some unseen force. One theory points to galactic fountains, where supernova explosions launch material high above the galactic plane, only for it to rain back down centuries later in altered form. Imagine a volcanic eruption spewing ash into the stratosphere, only for it to circle the globe and settle in unexpected patterns. These recycling loops could explain why certain elements appear in places no single supernova could have reached alone. The deeper we look, the clearer it becomes. Supernovae aren't just one-off fireworks. They're the galaxy's architects, weaving elements into the interstellar medium with a precision that still baffles scientists. From triggering new star formation to potentially seeding planets with life's raw materials, their echoes ripple far beyond their final moments. And somewhere in those whispers, we might just find the blueprint for how a galaxy grows, one catastrophic explosion at a time. Starlight travels billions of years across the cosmos to reach our telescopes, but when it finally gets here, it's changed. Not just dimmed or scattered, but fundamentally altered, as if space itself has twisted it. This is the puzzle of polarized starlight, where waves of light arrive with their electric fields aligned in eerie unison, like soldiers marching in perfect formation. The interstellar medium is the culprit, imprinting its secrets onto every photon that passes through, and what it's telling us could rewrite how we see the universe's hidden architecture. The first clue lies in dust, those tiny interstellar grains we once thought were just cosmic debris. As starlight encounters these particles, something peculiar happens. Irregularly shaped grains, like microscopic cosmic driftwood, don't just block light, they spin it, forcing the light waves to vibrate in a preferred direction. Picture sunlight glinting off the surface of a lake at dawn, with ripples aligning the reflections into a shimmering path. That's polarization in action, and in space, it reveals the hidden contours of dust we'd never see otherwise. The twist, the degree of polarization betrays the grain's shapes. Needle-like particles produce stronger polarization than spherical ones, suggesting the interstellar medium is littered with exotic, asymmetrical structures, some stretched by magnetic fields, others sculpted by ancient stellar winds. But dust isn't working alone. Magnetic fields, those invisible threads weaving through the galaxy, play puppeteer to this cosmic light show. As dust grains drift, they align themselves along magnetic field lines like compass needles, all pointing in the same direction. When starlight passes through this regimented army of particles, it emerges polarized, carrying a map of the magnetic landscape. The implications are staggering. By measuring polarization patterns, astronomers have traced magnetic fields looping around star-forming regions, twisting through supernova remnants, even stretching between galaxies. In some cases, the fields are so coherent they defy models of interstellar turbulence, as if an unseen hand combed them into order, yet mysteries linger. Some regions polarize light far more than expected, while others barely leave a fingerprint. The darkest, densest clouds, like Barnard 68, exhibit bizarre polarization holes where the signal drops to near zero. One theory suggests ultra-fine dust or exotic molecular coatings might be scrambling the light, like frosted glass diffusing a flashlight beam, another possibility. Magnetic fields in these zones are so tangled, their effects cancel out, leaving starlight untwisted. It's like trying to read a compass in a room full of magnets. Chaos obscures the true direction. The most tantalizing revelations come from combining polarization data with other cosmic clues. When paired with radio observations, polarized starlight has unmasked magnetic reconnection, events places where field lines snap and realign, unleashing bursts of energy. Other studies use it to hunt for dark matter, theorizing that certain interactions might subtly alter polarization patterns in ways we're only beginning to detect. Every new measurement adds another layer to the puzzle, proving that even the faintest twist in starlight can illuminate the universe's darkest corners. So the next time you look up at the night sky, remember, the stars aren't just shining. They're whispering, their light encoded with stories of magnetic storms, cosmic dust factories, and forces we've yet to name. And with every polarized photon, the interstellar medium hands us another piece of its grand, unsolved puzzle. some corners of the interstellar medium don't just avoid making stars, they seem to actively resist it. These eerie dead zones sprawl across galaxies like cosmic deserts, vast stretches where gas lingers for billions of years without collapsing into new suns. At first glance, they look no different from bustling stellar nurseries, same density, same temperature, yet they remain frozen in time, as if some invisible hand pressed pause on the universe's star-making machinery. What's silencing these regions? The answer might rewrite everything we know about how galaxies evolve. Take the Coalsack Nebula, a dark smudge near the Southern Cross so devoid of stars that ancient cultures saw it as a hole in the sky. Modern telescopes reveal it's packed with enough gas to birth hundreds of suns, yet not a single young star flickers within it. Traditional models blame turbulence, random motion in the gas that counteracts gravity's pull. But here's the problem. Some dead zones show remarkably stable gas flows with turbulence levels no different from active star-forming regions. Something else is at work, something that doesn't fit the textbooks. One leading suspect, dark matter's shadowy influence. Computer simulations suggest certain configurations of dark matter could create gravitational knots that act like cosmic roadblocks, preventing gas from reaching the densities needed to ignite stars. Picture trying to light a campfire in a stiff breeze. No matter how much kindling you pile up, the wind keeps scattering it before flames can take hold. If dark matter's unseen pull is disrupting these zones, it could explain why they stubbornly resist stellar births despite having all the right ingredients. Then there's the wild card of magnetic monstrosities. Observations of the Taurus molecular cloud revealed dead zones with magnetic fields so strong, they effectively pin gas in place like bugs trapped in amber. These fields don't just resist collapse, they channel gas into bizarre, thread-like filaments that refuse to fragment into stars. It's as if the universe wove an invisible net across these regions, one that lets gravity tug but never tear. The strangest part, some of these magnetic cages appear too organized to form naturally, hinting at processes we've yet to uncover. But the most unsettling possibility is that dead zones aren't failures at all, they're waiting. Some theorists suggest these regions could be cosmic pressure valves, places where the interstellar medium stockpiles material until triggered by a passing shockwave or galactic collision. The LDN 16-2 nebula supports this idea, a seemingly dormant cloud that abruptly began forming stars after a nearby supernova's shockwave brushed past it. Like seeds lying dormant until forest fires crack their shells, these zones might just need the right catastrophe to awaken, yet for every clue, dead zones deepen their mystery. Recent radio surveys have spotted a few that emit faint, unexplained energy signatures, neither star formation nor pure silence, but something in between. Are these the whispers of failed protostars that collapsed into black holes without ever shining? Or could they be markers of exotic physics, places where dark matter interacts with normal matter in ways we've never detected? Until we peer deeper into these cosmic stillness, they'll remain the interstellar medium's most unsettling open secret, not just empty spaces, but spaces deliberately kept empty, as if the universe itself forgot to hit play. Scattered across the interstellar medium like cosmic spider silk, vast filaments of gas stretch for hundreds of light years, delicate threads weaving through the darkness with eerie precision. These aren't random tendrils, they're uncanny echoes of the universe's largest-scale structure, the cosmic web. But here's what defies logic. While the cosmic web forms through the slow pull of gravity over billions of years, these interstellar filaments appear too quickly, too perfectly, as if space itself has a hidden blueprint for building bridges between the stars. Take the integral-shaped filament in the Milky Way's core, a river of molecular gas so straight and uniform, it looks like it was drawn with a ruler. Gravity alone can't explain its razor-sharp edges or the way it threads between stellar nurseries like a cosmic freeway. Turbulence should have shredded it eons ago, yet there it stands, defying chaos. The leading theory, magnetic fields, those invisible architects of the interstellar medium, might be acting like cosmic looms, spinning and aligning these structures with forces we're only beginning to measure. Imagine dropping iron filings near a magnet. They'd snap into orderly lines almost instantly. Now scale that up to galactic proportions, and you've got a potential recipe for these mysterious filaments. But magnetism isn't the only suspect. Some filaments glow with the faint energy of cosmic rays, hinting at another bizarre possibility. They could be scars from ancient supernova shockwaves. When a star explodes, it doesn't just vanish, it sends ripples through the interstellar medium, compressing gas into sheets and strands like frost crystallizing on a windowpane. The Rosette Nebula offers a stunning example where filaments radiate outward from a central cluster of young stars like spokes on a wheel, each one tracing the path of a long-ago stellar explosion. Yet even this explanation falters when faced with filaments that curve and braid like celestial DNA. Their structures too complex for simple shockwaves to explain. The real cosmic twist comes when you compare these filaments to their gargantuan cousins in the cosmic web. Both share the same skeletal structure, thin threads connecting dense nodes, but the similarities might run deeper than mere shape. Recent simulations suggest that the interstellar medium's filaments could be miniature versions of the universe's large-scale web, governed by the same underlying physics. In this view, dark matter's gravitational pull sketches the cosmic web's broad strokes, while magnetism and turbulence sculpt the fine details within galaxies. It's as if the universe operates on fractal rules, repeating patterns from the largest scales down to the tiniest tendrils of gas. Yet for every parallel, there's a glaring inconsistency. Some interstellar filaments pulse with periodic bursts of star formation, as if they're breathing life into the galaxy. Others, like the Musca molecular cloud, stand eerily dormant, a frozen rope of gas resisting collapse for millions of years. If these structures truly mirror the cosmic web, why do their fates diverge so dramatically? The answer might lie in the unseen interplay between dark matter and ordinary gas, or perhaps in quantum processes playing out across light years. One thing's certain, these filaments are more than cosmic decoration. They're the universe's hidden highways, channeling gas into stellar nurseries, feeding black holes, and maybe even seeding the chemical ingredients for life. Every time a telescope unveils a new thread in this grand tapestry, we're left wondering, are we seeing the handiwork of known physics, or clues to a deeper order waiting to be decoded? Until we unravel their secrets, these silvery strands will keep threading through the darkness, stitching together the story of a galaxy built on invisible lines. What if the interstellar medium isn't just a chaotic soup of gas and dust? What if it's thinking? Not in the way we recognize, of course. No cells, no synapses, no beating hearts. But consider this, the ISM teams with self-organizing structures, complex chemistry that builds and rebuilds itself, and energy flows that mimic the rhythms of biological systems. Magnetic fields act like nervous systems, threading information across light years. Molecular clouds collapse and bloom with stellar birth, like cosmic cells dividing. Even the way certain molecules replicate and adapt in the void. Could this be the universe's quiet experiment in a different kind of life? The idea isn't as far-fetched as it sounds. On Earth, we've found extremophiles thriving in places once thought sterile, boiling vents, acidic pools, even the vacuum-hardened guts of meteorites. If life can cling to existence in those brutal corners, why not in the vast, dynamic turbulence of the interstellar medium? Some astrobiologists speculate that self-replicating molecular chains, forged in the icy mantles of dust grains, might evolve through cosmic rays and UV light, mutating, competing, even feeding on energy gradients. Imagine carbon chains that restructure themselves to absorb more radiation, or silicate grains that catalyze reactions to prolong their stability. Not life as we define it, but something stranger, a shadowy, slow-motion dance of chemistry and physics operating on timescales we can barely fathom. Then there's panspermia, the wild hypothesis that life hitchhikes across galaxies seeded by comets or drifting spores. But what if the ISM itself is the gardener? Radioactive isotopes and organic molecules woven into dust grains could act as cosmic incubators, protecting fragile precursors to DNA as they drift between stars. Recent lab experiments show amino acids surviving interstellar conditions when shielded by ice. Now stretch that idea further. If the medium can assemble and preserve life's ingredients, could it also direct them? Magnetic fields might funnel organic, rich dust toward habitable planets, like a river carrying seeds to fertile soil. Sci-fi has danced with this notion for decades. Stanislaw Lem's Sentient Ocean in Solaris, or the Rogue Intelligence in 2001, A Space Odyssey. Yet the truth might be subtler. The ISM doesn't need consciousness to be alive in a cosmic sense. A forest isn't aware of itself, yet it breathes, grows, and regenerates. Could the interstellar medium operate on similar principles? A sprawling, galaxy-wide metabolism where stars are its energy vessels and supernova its renewal cycles. Here's the kicker: if the ISM is somehow alive, it would force us to redefine life itself. No longer bound to planets or chemistry as we know it, but as a universal phenomenon emergent from the raw logic of physics. Until we find proof, or until the void decides to whisper back, this remains the ultimate interstellar mystery. Not just how life survives in the universe, but whether the universe itself is built to create it. From ghostly dark gas clouds to rogue molecules defying chemistry itself, the interstellar medium is a cosmic hall of mirrors, reflecting back far more questions than answers. We've peeled back 25 of its deepest enigmas, and yet with each discovery, the universe seems to laugh, revealing 3 more puzzles hiding just beneath. Think about it. We're surrounded by invisible oceans of helium that vanish without a trace, mazes pulsing like interstellar lighthouses with no clear source, and filaments so perfectly sculpted they could pass as the universe's own handwriting. Even the empty spaces between stars whisper secrets, cold spots chilling beyond physics limits, dead zones resisting star formation with unnatural stubbornness, and carbon chains surviving radiation that should shred them to atoms. What makes these mysteries so thrilling isn't just their complexity, it's their intimacy. Every atom in your body was once part of this chaotic, creative medium, forged in stellar explosions and sculpted by forces we're only beginning to trace. When you look up at the night sky, you're not just seeing stars, you're staring into the universe's workshop, where the raw materials of existence twist into shapes that still baffle our brightest minds. And here's the beautiful truth: some of these riddles won't be solved by billion-dollar telescopes or supercomputers. They're waiting for someone like you, someone who gazes at the cosmos with fresh eyes and asks, what if we've been missing something obvious all along? Maybe the answer to polarized starlight's secrets lies in an experiment you'll dream up tomorrow. Maybe the key to supernova echoes is hiding in data we've already collected, overlooked until now. Or perhaps the interstellar medium's greatest surprise hasn't even crossed our collective imagination yet. That's the magic of science. Every mystery is an invitation, a door cracked open just enough to let curiosity slip through. So tell us, which of these cosmic conundrums keeps you up at night? The vanishing lithium, the impossible cold spots, or something we didn't even mention today? Drop your thoughts below, because the next great discovery might not come from a lab or a lecture hall. It might start right here with a spark of wonder from someone watching this very video. After all, the universe didn't put these puzzles there to stump us forever. It left them as breadcrumbs waiting for the right mind to follow the trail.